Right, this is video 3 for the types of nuclear, or for the chain reactions unit. So in this one, we're going to take a look at some types of nuclear reactors. The first type is called the light water nuclear reactor. So with this one, it's actually just like the picture I showed above, where we have a reactor that's heating up water, which then turns into steam, which blows across turbines, which then generates electricity. The steam is then condensed down by water, and then that water gives those great big cooling towers. And then the water then comes back to the steam generator, and so on and so forth. So this uses normal water, not heavy water, and the moderators slow neutrons without absorbing them. So basically, with this design, it's a very, very simple design, and this is the most common nuclear reactor that we have in the U.S. It's kind of a flawed design. It uses uranium, which is very expensive, and it just kind of well, as it uses the uranium, it gets used up, and it produces nuclear waste. But it's again, it's a very simple design and it's easy to build. The next type is the breeder reactor. Now, what's important for this one is that it generates more fissile material than it consumes. In other words, the waste from this reactor is actually fuel for other reactors. And that's very, 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 very important. In principle, this reactor could extract almost all of the energy contained in uranium or thorium. So the breeder reactor is a very, very cool design in that it it produces very, very little waste. The light water reactor makes a lot of waste. But the breeder reactor, its waste is fuel. It's important to realize, though, that there are some scientists now who are starting to try to make nuclear power plant designs that use the waste from the light water reactor, so that even that nuclear waste can be used to make electricity. Now, these two are the most common, the light water and the breeder. This next kind, the liquid fluoride thorium reactor, is purely theoretical. It's my favorite design. But what this does is it uses thorium and uranium-233. What's important to realize is that thorium is found in dirt. Thorium is very, very common. It's very, very cheap. And what happens is that this thorium and 233 are dissolved in a carrier salt. And then heat from that liquid salt is transferred to a non-radioactive liquid salt, which is then used to boil water. So this thorium and this 233 and this salt is very hot. Then the heat is transferred to a non-radioactive salt, which then boils water, and then the rest of it is just like any other nuclear power plant. Now, the reason why we use liquid salts is because they have to be very, very hot to stay liquid. The second they start to cool down, they turn into a solid. So in other words, if there's a problem, so if this nuclear reactor gets breached, it immediately hardens, and it's much, much easier to clean a solid than it is to clean a gas or a liquid. So these designs are extremely safe. You don't need that great big cooling tower. You don't need all of the extra safety precautions that are associated with nuclear power. The next type is another theoretical one. This is a fusion reactor. So for elements lighter than iron, the fusion reaction is exothermic. So heat can be used to boil water. So again, this fuses, and what this does is it uses lasers. So it uses lasers to generate the heat to fuse lighter elements such as deuterium and tritium. And then the goal is that that fusion then releases more energy than was needed to create the fusion, so we can use that extra heat to generate electricity. And there have been some gains in nuclear fusion reaction. So that's another promising one. So these last two, the liquid fluoride and the fusion reactor, are two theoretical reactors that, if we can build them, show a lot of promise. All right, now for the nuclear waste, the fission fragments from uranium all comes from uranium, so their weight is comparable. So a year of operation for a nuclear power plant will produce about 1 ton of fission fragments. We call this nuclear waste. It's potentially valuable for fuel and other reactors, but right now we're still developing those reactors, so it's still waste. Now, right now, all of the waste that we generate is stored on site, and we build these special containers, and we place the nuclear waste in these containers. And in many ways, it's kind of harmless. If you go around measuring the radioactivity around these containers, it's the same as the natural background radiation. And it's kind of important that we do this because now we have this material that could potentially be fuel for future reactors. So if we were to try to, shoot it off into space or bury it or something, it would be lost to us. So it's actually kind of better that we keep it on site. Now, I know that it seems like a lot of nuclear waste, like a ton per year, but really a ton is not that big, and because this stuff is very dense, it has a very low volume. You could fit all of our nuclear waste on a football field. So it's honestly not as much material as you might think. But it is something we need to deal with. Now, there have been 3 main nuclear disasters. There have been other smaller ones, but these are the biggest ones. So first off, we have 3 Mile Island. It was the worst nuclear accident in the U.S. And it happened in 1979. So what happened was it began when pumps that fed external cooling water to the reactor failed. The backup pump had a valve that someone had left closed. So the backup pump did not work. We then used control rods to stop the reaction. Control rods are carbon rods. And whenever you stick carbon into this reactor, it absorbs all the neutrons, so it stops the reaction. However, the residual heat, or the energy from those fission fragments, continued the heat. So what happened is about 1/3 of the core melted. Luckily, the steel container did not. So we were able to prevent this from really escaping into the environment. So that was the worst nuclear disaster in the U.S. Chernobyl was probably the most dangerous or the worst one of all time. Happened in 1986, and so what happened was this one used carbon as a moderator. So during a test of the safety of the reactor, the chain reaction grew out of control. And what happened was heat from this reaction then turned the water into steam and made a steam explosion. The carbon from the moderator caught on fire, and we believe about 5 to 30% of the fission fragments were carried away by smoke. And this is probably the most damaging part because it irradiated a large part of the surrounding areas because these fission fragments, which are radioactive, were carried away. And again, this was the most dangerous or the largest nuclear explosion or nuclear reactor failure ever. Nothing's ever come close to this one. And it's also important to realize that the Chernobyl design, even during the time it was constructed, never would have been built in the U.S. because it would never have met our safety regulations. The steam explosion, they did not have a very good containment building around their reactor to contain that steam explosion. So this Chernobyl never would have happened in the United States. Now, the Fukushima Daiichi, this one is the most recent. So in this one, it happened in 2011. And basically, what happened was a major earthquake and a 15-meter tall tsunami disabled the power supply cooling 3 reactors. And this is what caused the nuclear accident. So all 3 cores largely melted in the first 3 days. What's important to realize, however, is that while the earthquake and the tsunami did kill some people, no deaths or causes of radiation sickness. There have been no deaths or causes of radiation sickness from this nuclear accident. So in many ways, while this one's a large disaster, it's very fortunate that no one really got hurt because of this nuclear reactor. The people who did get hurt were, got hurt because of the earthquake and the tsunami. And really, this is Fukushima is actually a success story. There was more than just 3 reactors, and the majority of them survived an earthquake and a tsunami. So, really, it's a miracle. Well, not a miracle, but a good showing of engineering with this. Okay, so this is going to conclude our unit on chain reactions, nuclear reactors, and atomic bombs. In our next unit, we will start talking about electricity and magnetism.